Okay, we are in the position where we can finally start talking about the main idea of this course, which is the derivative. So let's recall from before that we saw that if we have some function y equals f of x, we can take the line connecting 2 points P and Q here, where in this case we'll say P is equal to B f of B and Q is equal to C f of C. And the slope of this is just the change in y over change in x. So f of c minus f of b over c minus b. And I've put the subscript pq on the slope to just indicate it's the slope of that secant line between p and q. Now the tangent line at the point AF of A is the line that all of those secant lines get closer and closer to as that P and Q both get closer and closer to AF of A. So here's an illustration of what's going on. So the A there is the purple, AF of A is the purple point there. And we can see those secant lines getting closer and closer. And then as they get kind of to the purple point, they become the tangent line. So now we can actually now that we know what limits are, we can actually formally define what that means. So we say the slope of the tangent line of f of x at the point AF of A is given by the limit as x goes to a of f of x minus f of a over x minus a, if the limit exists. There will be cases when this limit doesn't exist, and then we don't have a slope of a tangent line there. Another thing to note here is that this is the slope of the tangent line. Saying it's the slope of the function doesn't make any sense because basically there's no such thing other than the slope of the tangent line. So always make sure we're careful in saying it's the slope of the tangent line at AF of A. And it'll often be easier to actually use this separate formula for calculating the slope. So in this case, we'll replace x with a plus h, and then as h goes to 0, a plus h goes to a. So we can replace that x goes to a with h goes to 0. The reason this will be easier is that it's going to be easier to factor in h out of the numerator to cancel with the bottom, as we'll see later, than it is to factor in x minus a out of the numerator of the first version. So either version is fine in terms of the definition, but we'll usually use the second one, though we're going to give one example with the first definition as well. So let's start with this one, y equals x squared at the point 2, 4, and we'll use that first definition as x goes to a for this one. Okay, so if we want the tangent line, we need a point and a slope. That's how we give a line. So we know the point already. We're told we want the point to be 2, 4. So we're going to use our definition of a derivative to figure out what the slope is. So here we have that the slope is the limit as x goes to 2 of x squared minus 4 over x minus 2. And the important point here is we can factor the numerator there to be x minus 2 times x plus 2. And then we can cancel that x minus 2 out as long as x is not equal to 2, as we saw in the previous section. So that just gives me the limit as x goes to 2 of x plus 2, which is just equal to 4. So the slope of our tangent line is going to be 4. So that means our tangent line is just given by y minus 4 is equal to 4 times x minus 2. So using the point slope formula for the equation of a line. And here's a picture of this. So we have our graph y equals x squared there. And we can see if we go over to the point 2, 4, we have this tangent line. Y minus 4 is equal to 4 times x minus 2 there in purple. So the slope of the tangent line is giving you the rate of change of the function at AF of A. So there's situations where we don't necessarily want to phrase this in terms of slopes of tangent lines. We just are interested in the rate of change of a function without thinking of the geometry of it. So in this case, we'll just define the derivative rather than just the slope. So the derivative at x equals a is the limit as x goes to a of f of x minus f of a over x minus a. Or equivalently, we can phrase it as h goes to 0 of f of a plus h minus f of a over h. And notice the notation for this is f prime of a. So we put a prime on the f to denote the derivative. And we say the function is differentiable at x equals a if this limit exists. So it won't always be the case the limit exists. We'll see an example later. But when it does, we say it's differentiable there. And then this is the definition of the derivative. So let's see an example where this limit doesn't exist, just so we see kind of what can go wrong here. So let's consider the absolute value function. So remember, the absolute value function is given by absolute value of x is x if x is non-negative, and it's negative x if x is negative. That negative sign makes the value positive. So think of, like, for example, if x were -2, negative 2 becomes positive 2, which is what we would want for the absolute value of -2. So now let's see what's happening at this point 0, where we're kind of changing what our definition is. So let's calculate the limit coming from each direction. So we'll start with the left-hand limit. So we use our function here. So f of 0 plus h is absolute value of 0 plus h, minus f of 0, which is absolute value of 0. So this just gives me the limit as h goes to 0 from the left of absolute value of h over h. Now, since we're saying that h is coming to 0 from the left, that's telling us h is a negative number. So that means absolute value of h is negative h. So I get the limit as h goes to 0 from the left of negative h over h. Well, that h in the top and the h in the bottom cancel, so we just get limit as h goes to 0 from the left of -1, which is just -1. And if we look at the right-hand side, everything works out the same, except for, since we're coming from the right-hand side, the absolute value of h is just h, so our limit becomes 1. So we see, coming from the left and the right, we get two different limits, so that means the limit doesn't exist. And since that limit doesn't exist, the function's not differentiable. So let's look at a picture to see what's kind of going on here. So notice, as we're coming to 0 from the left, the function is just y equals negative x, which is just a line with slope -1, which is kind of what we calculated. If we're coming from the right, it's the line y equals x, which has slope 1. And then at the origin there, we see we have this sharp point where we drastically change directions. So if we're thinking in terms of tangent lines, if we were at 0, there'd be no way to define what is the slope of a tangent line there. And this is going to be true in general with functions. Whenever you have a sharp point like that, the function is not going to be differentiable at that point. So we can keep that in mind for later when we see different graphs where there's sharp points. Anytime there's a sharp change of direction like that, it's not differentiable there. You can always think about what would the slope of the tangent line be. If there's no way to define a slope of a tangent line at a point, then it's not differentiable. So now let's try one where we can find the derivative. So let's calculate the derivative of this function 1 over x squared at the point x equals 2. So we'll use our second definition where we take the h goes to 0. And so here we take f of 2 plus h minus f of 2 over h. So if we plug that in, I get 1 over 2 plus h squared minus 1/4 over h. Then we can FOIL out the 2 plus h squared to get 1 over 4 plus 2h plus h squared minus 1 over 4. And now we need to simplify the numerator there. So what we're going to do is we get a common denominator. So we multiply the first term by 4 in the top and the bottom, and the second term by 4 plus 2h plus h squared in the top and the bottom. And so now we're going to bring this fraction together in the numerator to try to simplify it. So if we bring that together and then we go ahead and take the denominators and combine the denominators. So I get 4 minus 2h minus h squared over h times 4 plus 2h plus h squared. The 4's in the numerator cancel, and then I have minus 2h minus h squared. I can factor a minus h out of that to leave me with 2 plus h. And then notice that h minus h in the top and then h in the bottom, I can cancel those off. So in the numerator, I'm just left with minus 2 plus h. And in the denominator, I'm left with 16 plus 8h plus 4h squared. And now I can just go ahead and plug h equals 0 into this, and I get a negative 2 in the top, I get a 16 in the bottom, and if we simplify, we get minus 1/8. So when you're calculating derivatives using this definition, it's almost always going to be the case that we need to simplify it so we get an h that we can factor out of the numerator to cancel that h in the denominator. Okay, so we've seen that if I have a function that is differentiable, then I can associate this number f prime of a. And geometrically, this is giving me the slope of the tangent line at the point AF of a. But we've also saw for each time we do this, we have to calculate this limit for every value of a. So if in the previous example we did for 1 over x squared, we wanted it at x equals 2, if you finish that calculation, I asked you, okay, what's the slope of the tangent line where x is equal to 3? You'd have to run through that entire calculation again. And that can be kind of tedious. So what we're going to do is we're going to define a derivative function where we calculate the derivative for any value of a so that we can just plug into our final answer for any a that I happen to give you. So let's suppose I was looking at the function f of x is equal to x squared, and just rather than picking a particular constant, let's just take any constant a. So if I run through this same calculation, I take the a plus h squared minus a squared, FOIL the first term off, I cancel those a squareds off, I factor an h out, cancel the h's, and then I end up with seeing this is just equal to 2 times a. And the benefit of this is if I ask you now, well, what's the slope of the tangent line at a equals 2, you can just plug in and see it's 4. If I ask you for the slope of the tangent line at a equals 10, you can just plug in and see that that's 20. So it saves quite a bit of time. You do a calculation one time, and then you're essentially done, and you can just plug in after that, make it much easier. So we're going to consider this a new function and just say f prime of x is equal to 2x, and then notice if we plug in any constant a, we get 2a just like our calculation above. So that's going to be our definition of the derivative where we view it as a function now. So we have f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. So this looks like exactly like we did before. We've just changed out the a for an x. And so now this is a function where we can input values, whereas before f prime of a was a number. So a couple of other notations we can use for this is we can write it as df over dx or dy over dx. These second versions of this notation, the df over dx and dy over dx, are a little bit more suggestive of what's going on because they're saying the change in f or the change in y over the change in x. So how is f or y changing as you change x? So it's a little bit more illustrative of what we're actually doing, but it's a little bit more cumbersome to actually use. But we'll switch back and forth between the notations just to make sure you're used to both of them. Okay, so like I said, we've calculated these at individual points. If we're doing this, we've done it all at once, so we can just plug the values in. So that's really one of the reasons we're doing this, is to save ourselves some effort. So let's think about what this derivative function is giving us graphically. So consider my function here, y is equal to f of x. And we can go ahead and graph the derivative function over the top of this function. So here is the graph of y is equal to f prime of x. And so let's see how we went about getting this function. So remember, the value of the derivative at any point happens to be the slope of the tangent line at that point. So a couple of points we can pick out right away are the points where the slope of the tangent line would be 0. So those are where the tangent line would be horizontal. So notice here at these 2 points where we've indicated with the red dashed lines, the tangent line to the blue graph there is a horizontal line there. So the derivative will be 0. So we can go ahead and, when we're trying to graph the derivative, note that those are the points where the derivative will cross the x-axis. And now, between those 2 red dashed lines, the slopes of those tangent lines there are always going to be negative. So we can tell, well, our derivative graph then has to be below the x-axis. And we can also see there at the origin, that's where it's the steepest, so the most negative. So that's where the derivative graph should be the furthest down the y-axis. And then after that, it kind of turns around and comes back towards 0 if we're looking at slopes of tangent lines. And once we get past this line that looks like it's just a little bit past 3, now the slopes of the tangent lines are positive and getting more positive, so getting bigger. So our function's increasing in positive there, and similarly for the left-hand side. So make sure you take a few minutes here before you stop the video and understand where we're getting that graph f prime of x from by just looking at some tangent lines and the slopes of those tangent lines to see what's going on.